In this section, we begin the study of the core idea of the calculus, the concept of limit. We have already talked about the limit of a sequence in a previous lecture. Now we discuss that idea in full detail and introduce the idea of the limit of a function f of x as x tends to some value. First, we talk about the limit of a sequence as n tends to infinity, and simultaneously about the limit of a function f of x as x tends to infinity. We say that the sequence an has a limit L as n tends to infinity if the terms of the sequence get close and stay close to L as n gets large. You tell me how close you want to stay to L. That is, give me a number epsilon greater than 0, and I must convince you that if you go far enough, I can find a natural number for that epsilon, call it cap n sub epsilon, emphasizing that it depends on epsilon. And then if you choose any term a sub n with n greater than n sub epsilon, the distance of an from L is less than your estimate of epsilon. Well, that's a mouthful for sure. It helps to develop a visualization of this mass of English language words. Fortunately for us, there are two very useful visualizations. In this picture, we have plotted the pairs n, an in the Cartesian plane. In other words, we really are thinking of the sequence as a function, an equals f of n, with domain the natural numbers. The limit L is pictured as a constant function. Think of the number epsilon as a very small number defining a tube of radius epsilon about the horizontal line y equals L. Then our definition of limit says that eventually, that is for n beyond cap n sub epsilon, the points n will all lie in the tube. If you change epsilon, then n of epsilon may have to change. This visualization is using the fact that the statement absolute value of an minus L less than epsilon is saying that the distance from the y-coordinate an to the number L is less than epsilon. Here is a second and more common way to picture the limit of a sequence. Here we plot the points an on the number line, and we plot the point L as well. Then the number epsilon determines the target interval L minus epsilon to L plus epsilon, an interval of length 2 epsilon centered on L. The statement that the limit of an is L means that for n large enough, that is n beyond some capital N that depends on epsilon, the terms an will all lie in the target interval. Notice that the sequence might hop in and out of the target interval before settling in. We really don't care. Also, the sequence may just sit on L. For example, the constant sequence 2 has limit 2 because every term is 2. The universal notation for the statement that the limit of an is L is lim n tends to infinity an equals L. And the rather wordy definition we have given can be stated in mathematical terms, succinct but somewhat intimidating, as lim an equals L if and only if, for all epsilon greater than 0, there exists an n sub epsilon such that n bigger than n sub epsilon implies absolute value of an minus L less than epsilon. Wow. There are two symbols for mathematical logic used when you write this down. The upside down A means for every, and the backwards capital E means there exists. The double arrow pointing in both directions means if and only if, or in this context, it is perhaps best interpreted as means. The symbol right pointing arrow means implies. Let's look at our picture again with the mathematical definition tied to that picture. Now we need to work through some simple examples to get a feeling for this definition. Consider the sequence 3 over n. If we plot this sequence as a Cartesian graph, then it seems clear that the limit as n tends to infinity of 3 over n is 0. Let's prove it. You have given me a tiny number epsilon, say 10 to the minus 26, and I have to convince you that the sequence is eventually with an epsilon of L equals 0. Well, let's begin with a more realistic specific value for epsilon, say 1/12. What we want is to find a natural number capital N such that for n beyond capital N, 3 over n minus 0 in absolute value is less than 1/12. The way to start is to look at the desired inequality, absolute value 3 over n minus 0 less than 1/12, and try to manipulate it into a statement about the size of n. We established in a previous lecture that the inequality, absolute value x minus a less than b, is equivalent to x minus a must be between minus b and plus b. This allows us to restate the desired inequality as 3 over n minus 0 is bigger than minus 1/12 and less than 1/12. And of course you can erase the 0 and write 3 over n must lie between minus 1/12 and 1/12. And since 1 over n is always positive, the left-hand inequality is always satisfied. So now I have to convince you that there is a number cap n such that if n is beyond cap n, 3 over n is less than 1/12. But we can use our rules for solving inequalities to show that this last inequality is equivalent to n bigger than 36. In plain English, the requirement that 3 over n be within 1/12 of 0 is equivalent to saying that we must have n bigger than 36. So we have demonstrated that we can safely choose capital N equal to 36 to guarantee that n bigger than capital N implies absolute value 3n minus 0 less than 1/12. Now we can go on this way, selecting a specific value of epsilon and showing that we can find a value n that works for that epsilon. Or we can use the power of mathematical symbolism to deal with all values at once. Being lazy, I opt for the latter. Suppose epsilon has been given. We want to establish a formula for n, depending on epsilon, so that when n exceeds capital N of epsilon, the absolute value of 3 over n minus 0 will be less than epsilon. We go to work on the desired target inequality, absolute value 3n minus 0 less than epsilon, which is equivalent to 3 over n minus 0 must lie between minus epsilon and epsilon. As before, we can erase the 0 and observe that the left-hand inequality is always satisfied because 3 over n is positive. Therefore, the desired target inequality becomes 3 over n less than epsilon. We can solve this for n. N must be bigger than 3 over epsilon. Now 3 over epsilon is not in general going to be a natural number, but that's okay. Just choose cap n sub epsilon to be any natural number larger than 3 over epsilon. And then, if little n is bigger than cap n sub epsilon, it will also be bigger than 3 over epsilon, and that's equivalent to our desired inequality, that the distance between 3 over n and 0 be less than epsilon. To recap, we wrote down the formal definition for our specific sequence. Then we worked on the desired target inequality to show that it is equivalent to a statement about the size of n, and we used this statement to choose cap n sub epsilon. Another example. Consider the sequence 3n divided by n plus 2. If we plot this in the Cartesian plane, it seems to be tending to 3. In fact, if we divide numerator and denominator by n, we get the equivalent form 3 divided by 1 plus 2 over n. Since we expect 2 over n to go to 0 as n tends to infinity, it looks very much like our sequence converges to 3. To prove it, we write out the formal definition. N bigger than capital N of epsilon should imply that the ratio 3n to n plus 2 minus the number 3 in absolute value should be less than epsilon. Now we restate the target inequality. 3n divided by n plus 2, subtract 3, must lie between minus epsilon and epsilon. Now we have to work with both inequalities and see what they have to tell us about the size of n. We add 3 to all the terms, and then multiply through by the positive number n plus 2 to get the equivalent inequalities. 3 minus epsilon times n plus 2 must be less than 3n, which in turn must be less than 3 plus epsilon times the quantity n plus 2. We solve the left inequality for n, and it tells us that n must exceed 2 times 3 minus epsilon over epsilon. So this is our first restriction on n, given any value of epsilon. We solve the right inequality to get that n must exceed minus the ratio 2 times 3 plus epsilon over epsilon. This is always true since n is positive and the left side is negative. So given an epsilon, the target inequality will be satisfied if n exceeds the number 2 times 3 minus epsilon over epsilon. And so we can choose cap-ents of epsilon to be any number larger than the right side of this inequality. And we have proved that the limit is indeed 3. We can do the same kind of analysis with functions. First, we define the idea of the limit of a function as x tends to either of plus infinity or minus infinity. The limit as x tends to plus infinity of f of x equals L is equivalent to saying that for every epsilon greater than 0, we can find a number capital B of epsilon such that x bigger than b of epsilon implies the absolute value of f of x minus L is less than epsilon. Dually, the limit as x tends to minus infinity of f of x equals L means that for every epsilon greater than 0, there is a number capital B of epsilon such that x to the left of b of epsilon implies the absolute value of f of x minus L is less than epsilon. In the first definition, with x tending to plus infinity, we're thinking of capital B of epsilon as a large positive number beyond which the graph of f of x stays in a tube of radius epsilon about the constant function y equals L. In the second definition, with x tending to minus infinity, we're thinking of b of epsilon as a large negative number such that if x is to the left of b of epsilon, then the graph of f of x stays in an epsilon tube about the constant function y equals L. You have already seen limits at infinity in another context. The number L is a horizontal asymptote for the function f of x, if and only if one of the limits at plus infinity or minus infinity is L. As an example, let's look at the limit as x tends to plus infinity and the limit as x tends to minus infinity of the ratio absolute x over x plus 2. Don't panic over the absolute value. That just means that the function is defined differently for positive x and negative x. Namely, f of x is equal to minus the ratio x over x plus 2 if x is less than or equal to 0. And f of x is equal to the ratio x over x plus 2 if x is greater than or equal to 0. We can graph the function to get a clear idea of what happens as x tends to plus or minus infinity. When we are dealing with questions of limits at x equal plus or minus infinity, it often helps to divide numerator and denominator by the largest power of x in sight. If we do that, we see that the definition of this particular function becomes f of x equals minus the ratio 1 to 1 plus 2 over x for x negative. F of x equals plus the ratio 1 to 1 plus 2 over x if x is positive. It is intuitively clear that 1 over x goes to 0 as x goes to plus or minus infinity. If we accept this, then it appears that the limit as x tends to minus infinity of f of x is minus 1, and the limit as x tends to plus infinity of f of x is plus 1. Let's prove it for x tending to minus infinity. We want to show that for any epsilon, there is a number b of epsilon, such that x less than b of epsilon implies that the absolute value of f of x minus the number minus 1 is less than epsilon. Exactly as we did with sequences, we take the target statement and try to find out what it tells us about restricting x. F of x minus minus 1 less than epsilon is equivalent to f of x plus 1 lying between minus epsilon and epsilon. Now, since we are examining the situation x tending to minus infinity, we can certainly assume that x is negative and use the corresponding formula for the function for x less than 0. Our inequalities then become minus epsilon less than minus the ratio x to x plus 2 plus 1 less than epsilon. Now we can solve each inequality for x, but be careful. X is assumed large or negative, so x plus 2 will also be negative, and that will flip the inequalities if you multiply through by x plus 2. Let's solve the left inequality step by step. First, subtract 1 from both sides. Now multiply by minus 1 to reduce the confusion, and remember to flip the inequality. Now multiply by the negative number x plus 2, which again flips the inequality. And finally, solve for x. The restriction is x must be less than minus the ratio 2 times 1 plus epsilon divided by epsilon. This is a perfectly reasonable restriction on x, and you can choose capital B of epsilon equal minus the ratio 2 times 1 plus epsilon over epsilon to satisfy this first constraint. But now the right-hand inequality must be satisfied as well, and it must be solved then. The result is x less than twice 1 minus epsilon divided by epsilon. This is always satisfied if epsilon is less than 1, since x is negative and the right side is positive. You might ask, what if someone gives you an epsilon bigger than 1? Just tell them you'll do even better than they ask. You will keep the values of f of x within 1/2 of the limit. Here is a picture of what we have done. In addition to looking at the limit of a function as x tends to plus or minus infinity, we can look at the limit of a function as x approaches any number a on the real number line. This is important, for example, for analyzing rational functions like absolute value of x over 2x near x equals 0, or x cubed minus 8 divided by x minus 2 near x equal 2, or functions like sine x over x near x equals 0. The only change from what we have been doing with limits at infinity is that we now talk about what happens as x gets closer and closer to a, rather than being concerned with what happens as x gets large moving to the right or large moving to the left. This means we don't talk about x bigger than some number capital B or x less than some number capital B, but rather measure the distance from x to a. And the way to measure that distance is to use the absolute value of x minus a. Also, we will need to take account of the fact that we can approach a from either side. If the limit is L, as x approaches a from the right side, we write lim x arrow a plus f of x equals L. Or sometimes we use the symbol x downward pointing arrow a. For an approach from the left, we use the symbol x right pointing arrow a minus or x upward pointing arrow a. Before we finally state the formal definition, let's look at some simple examples and determine the limits involved by using common sense. So consider f of x equals absolute value of x over 2x. This function is defined by different formulas for x negative and x positive. F of x is minus x over 2x for x negative, and that just reduces to f of x equals minus 2 for x negative. The function is undefined when x is 0. Why? The function for x positive is just x over 2x, which is just 2. We can graph this function. The circle indicates a hole in the graph where the function is undefined. In this case, the reason is that the formula gives 0 over 0, which is undefined. It is clear that as x approaches 0 from the left, the values of f of x are always minus 2, and so the limit as x goes to 0 from the left is minus 2. From the right, the values of f of x are always plus 2, so the limit as x tends to 0 from the right is 2. Notice the value of f of x at x equal a is totally irrelevant, and the function doesn't even need to be defined there. To re-emphasize this point, we are interested in the values of f of x for x near but different from a. Let's look at another example. G of x equals x cubed minus 8 divided by x minus 2. The numerator factors, x cubed minus 8 is x minus 2 times x squared plus 2x plus 4. So at all points except x equal 2, g of x equals x squared plus 2x plus 4. At x equal 2, the function is undefined. The graph looks like this, where the circle again represents a point where the function is undefined. Now it is clear from the graph of g of x that if x approaches 2 from the left, the values of g of x approach 12, and the same is true if you approach from the right. Therefore, the limit as x tends to 2 of g of x is 12. After mastering these two examples, we can state the formal definition. The limit as x tends to a from the right of f of x equals L means that for every epsilon greater than 0, there is a delta greater than 0, such that x minus a in absolute value positive and less than delta, and x to the right of a, implies that the distance between f of x and L is less than epsilon. Here's a translation into reasonably coherent English. If the limit of f of x as x approaches a from the right is L, then you can tell me how close you want to keep f of x to L by specifying a constraint on the absolute value of f of x minus L. This is the epsilon. Then I will always be able to provide you in return with a constraint on the distance between x and a, we call it delta, so that if x satisfies my constraint and is to the right of a, then f of x satisfies your constraint. Here's the picture. The definition for x tending to a from the left just replaces x greater than a with x less than a. If we want to talk about the limit as x tends to a of f of x, then we drop the requirement that x remain on one side of a. Let's use the formal definition to prove that the limit as x tends to 2 of 3x minus 1 is 5. We need to show that for every epsilon greater than 0, we can find a delta, which depends on epsilon, greater than 0, such that absolute value of x minus 2 positive and less than delta implies the difference between 3x minus 1 and 5 in absolute value is less than epsilon. As with sequences, we take the desired inequality, 3x minus 1 minus 5 less than epsilon in absolute value, and see what it tells us. In this case, it is not the size of n, as it was for sequences, that interests us. We need to see what this inequality tells us about x minus 2. So we get rid of the absolute values in that desired inequality in the standard way. Absolute value of 3x minus 1 minus 5 less than epsilon means that 3x minus 1 minus 5 lies between minus epsilon and plus epsilon. And 3x minus 1 minus 5 is just 3x minus 6. 3x minus 6 can be divided by 3. And so if we divide through all of the inequalities by 3, we get minus epsilon over 3 less than x minus 2 less than epsilon over 3. And that is equivalent to absolute value of x minus 2 less than epsilon over 3. So the required constraint, absolute value f of x minus L less than epsilon, turns out to be equivalent to absolute value of x minus 2 less than epsilon over 3. Therefore, we can choose delta equal epsilon over 3, and this will guarantee that f of x minus L is less than epsilon. Don't be discouraged if you find this hard. There are very few people, including a lot of mathematicians, for whom it was hard at first exposure. The way to master this is to work through a good number of examples. Finally, a word on functions that blow up. Consider the function h of x equal x over x minus 2, which is undefined at x equals 2. Here is its graph. From the graph and the formula defining the function h, we can see that h blows up to plus infinity as x tends to 2 from the right, and blows up, or maybe we should say down, to minus infinity as x tends to 2 from the left. A simple change in our earlier definitions gives a precise definition of these intuitive observations. For example, for the case when the limit is plus infinity as x approaches from the right, we need to think of the function as exceeding any given proposed limit k on its values. The limit as x tends to a from the right of h of x equals plus infinity means that for every positive number k, we can find a delta greater than 0, such that if x minus a is positive and less than delta, then h of x will exceed k. In other words, close enough to a, h of x will exceed k. In general, we won't use this formal definition and just depend on our intuition to decide on such limits.